Okay, geometry, section 2.1, conditional statements, part 1. So the first box that we spoke about was a conditional statement has two parts. Okay, it has two parts. It has a hypothesis and a conclusion. And sometimes the hypothesis is written in if-then form called biconditional form. So if is the hypothesis part and then is the conclusion part. So here's a little example that we came up with today. So if I go to Healdsburg High School, then I am a rad. This is an if-then statement. Here's the if part. Here's the then part. Okay, if I go to Healdsburg High School, then I am rad. So if we try to identify the hypothesis of the conditional statement, the hypothesis part is if I go to Healdsburg High School. This is the first part. Comes after the if. It's the hypothesis. The conclusion of this conditional statement is I am rad. So I am rad is the conclusion. If I go to HHS, Healdsburg High School, then that is the hypothesis. So that's the first thing that we did together in class today. Then we went down and we spoke about rewriting a statement in if-then form. And I gave two examples here. I said Levi's 501 jeans have a button fly. So that's just a statement. Levi's 501 jeans have a button fly. We changed it to a conditional statement by adding an if and then. So if you have Levi's 501 jeans, then you have a button fly. So the if you have Levi's 501s is the hypothesis, and you have a button fly, that is the conclusion. And then B says a number divisible by 5 ends in a 5 or a 0. So we again changed this to a conditional statement that said if a number is divisible by 5, then it ends in a 5 or 0. So this again is the hypothesis. This in blue is the conclusion. Okay, then we want to discuss that a conditional statement, that's what this part means, a conditional statement can be either true or it can be false. So if a conditional statement is true, then you have to present an argument or a proof or some kind of a mathematical way to show that your statement is true for all hypotheses, so all if parts. However, if it is false, you only have to find one counterexample. There's that word counterexample again that we came up with in chapter 1, okay? So then we spoke about the converse, the inverse, and the contrapositive. These three ideas here for negating a conditional statement. And I introduced this notation of P and Q. So I start off with a working example. Like say, here's my example is this. Okay, if a number is divisible by 5, hypothesis, then it ends in 5 or 0, conclusion. So what we did was we said everything in yellow is going to be P, and everything in green is going to be Q. So the original statement says if P, then Q. So if P, which is a number, is divisible by 5, then Q, it ends in 5 or 0. So then we decided we want to explore the converse, the inverse, and the contrapositive. The converse is written in shorthand, if Q, then P. So notice we just took the conclusion and made it the hypothesis, and took the hypothesis and made it the conclusion. So we switched them, and doing that is called the converse. So the converse of this statement would be if a number ends in 5 or 0, then it's divisible by 5. So this is the converse to our original statement. And notice I kept all the hypothesis in yellow and all the conclusions in green, but in this case they were switched around. Okay, they were switched around because it's the converse. So the inverse then is if not P, then not Q. So the little tilde out in front means not. So not P, then not Q. So to negate our statement P says if a number is not divisible by 5, then it does not end in a 5 or 0. And that is pretty true. So let's take the number 11 for example. 11 is not divisible by 5, nor does it end in a 5 or a 0. So that's okay. So that's called the inverse, by negating both the original hypothesis and the conclusion is the inverse. So we have converse, inverse, and finally we had contrapositive. And the contrapositive means switch both of them and negate both of them. So it would look like this. If not Q, then not P. And for our example, we said if a number does not end in a 5 or 0, then it is not divisible by 5. And we figured out that the original statement is the same argument as the contrapositive. So the original statement that we had way back up here, if a number is divisible by 5, then it ends in a 5 or a 0, is the exact same argument as saying this. If a number does not end in a 5 or 0, then it is not divisible by 5. Those two are logically equivalent. All right, then I gave this example for us, and we had a great debate in class today about this. And the original conditional statement said this: if an animal is a fish, then it can swim. We actually looked up the definition of swim, and it meant propelling through water by use of appendages. So, if an animal is a fish, then it can swim. And we all agree that this is a true statement. So I asked everyone to write the converse and the inverse and the contrapositive. So the converse was, if an animal can swim, then it's a fish. The inverse says, if an animal is not a fish, then it cannot swim. So if not P, then not Q. And finally, the contrapositive was, if an animal can't swim, then it's not a fish. And so we had a big time discussing whether or not this statement was true. Is this a true statement? If an animal can't swim, then it's not a fish. And we eventually realized that that is the same thing as the original statement. If an animal is a fish, it can swim. So we just agree that that was true. Then we got into some groups and did some group work. Okay, so that is the 2.1 conditional statements part 1.